Gas tungsten arc welding. Gas tungsten arc welding is also known as tungsten inert gas welding. It is an arc welding process that uses a non-consumable tungsten electrode to produce the weld. The weld area is protected from atmospheric contamination by a shielding gas, usually an inert gas such as argon, and a filler metal is normally used, though some welds, known as autogenous welds, do not require it. A constant current welding power supply produces energy which is conducted across the arc through a column of highly ionized gas and metal vapors known as a plasma. Manual gas tungsten arc welding is often considered the most difficult of all the welding processes commonly used in industry. The reason is because the welder must maintain a short arc length, great care and skill to prevent contact between the electrode and the workpiece. Gas tungsten arc welding normally requires two hands, since most applications require that the welder manually feed a filler metal into the weld area with one hand while manipulating the welding torch in the other. However, some welds combining thin materials, known as autogenous or fusion welds, can be accomplished without filler metal. Most notable examples being edge, corner, and butt joints. To strike the welding arc, a high-frequency generator similar to a Tesla coil provides an electric spark. This spark is a conductive path for the welding current through the shielding gas and allows the arc to be initiated while the electrode and the workpiece are separated, typically about 1.5 to 3 millimeters, that is somewhere around 0.06 to 0.12 inches apart. Once the arc is struck, the welder moves the torch in a small circle to create a welding pool, the size of which depends on the size of the electrode and the amount of current. While maintaining a constant separation between the electrode and the workpiece, the operator then moves the torch back slightly and tilts it backward about 10 to 15 degrees from vertical. After that, filler metal is added manually to the front end of the weld pool as it is needed. Welders often develop a technique of rapidly alternating between moving the torch forward, that is, to advance the weld pool, and adding filler metal. The filler rod is withdrawn from the weld pool each time the electrode advances, but it is never removed from the gas shield to prevent oxidation of its surface and contamination of the weld. Filler rods composed of metals with low melting temperature, such as aluminium, require that the operator maintain some distance from the arc while staying inside the gas shield. If held too close to the arc, the filler rod can melt before it makes contact with the weld puddle. As the weld nears completion, the arc current is often gradually reduced to allow the weld crater to solidify and prevent the formation of crater cracks at the end of the weld.
Like I want to tell about advantages and disadvantages of GTAW. So firstly, I want to compare the GTAW with SMOG. okay, with a shaded metal arc welding. Firstly, GTAW has higher quality welding, while small has low quality welding. The second is GTAW welding is mostly free from spatter, while small produce excessive spatter even with optimal set of process parameters. The third is the GTAW has higher cost of equipment, while small has low cost of equipment. So the first is advantages of GTAW is higher quality, where the weld results are stronger, where they can penetrate deeper and have higher corrosion resistance. So the second is welding results are very clean because they do not produce lag and do not produce spatter or welding sparks. Next is prevent fouling by nitrogen and oxygen, where the gas flow makes the area around the metal liquid not contain air, so that it prevents fouling by nitrogen and oxygen. Next advantages is the GTAW can weld more metals and alloys than any other process, such as stainless steel, chromoly, and aluminum. Next, the disadvantages. The first is slower travel speed than other process, such as in the diagram, the direction of travel to the right, where the welding need longer time to finish the welding. The next is hand-eye coordination is required skill, which is we need a professional to do the GTAW welding. And this next is brighter UV rays than other process. Such in the diagram below, we can see how brighter UV rays can produce while using the GTAW. The last is for this advantage of GTAW is equipment cost can be higher with other process, such and the diagram shows gas supply, electrical power source, connection cables, stands, electrode, pillar rods, and others.
The thing that I will discuss is about welding defect. So there are few types of welding defect, which is porosity, slack inclusion, incomplete fusion and penetration, weld profile, and the last is cracks. Okay, I will explain one by one. Okay, porosity is happen during welding metal absorb gases, high affinity to gases. Okay, when solidified, gases trapped in metal. So the large size of porosity we call it as blowhole. So this defect can be reduced by proper selection of electrodes and filler metals, improve welding techniques, proper cleaning, and the prevention of contaminants. The last is reduce welding speed. Okay, next is slack inclusion. The slack inclusion is causes from outside electrode coating or fluxes trap. Failure to remove slack leads to slack inclusion. With control of welding process parameters, the molten slack will float to the surface of the molten weld metal and thus will not become entrapped. Okay, this defect can be prevented by providing sufficient shielding gas, cleaning the weld bit surface, redesigning the joint to permit sufficient space for proper manipulation of the puddle of molten weld metal. Okay, next, the defect is incomplete fusion and penetration. This defect produces poor weld bits. So, this defect can be reduced by raising the temperature of the base metal, cleaning the weld area before welding, modifying the joint design, and the last is providing sufficient shielding gas. Okay, next is weld profile. It is important because its effect on the strength and appearance of the weld indicate incomplete fusion or the presence of slack inclusion in multiple layer welds. The last is cracks. Cracks occur in various locations and directions in the weld area. This crack is happen when this is because of temperature gradients, variation in the composition of the weld zone, embrittlement of grain boundaries, hydrogen embrittlement, inability of the weld metal to contract during cooling. Okay, this is how crack looks like.